Hello, everybody. How are we doing today? So we're gonna get to go on a bit of a beamline safari, as my professor likes to call it, because today I'm gonna start showing you guys my senior research project. So I'm gonna go ahead and set us a timer for about 30 minutes, and we will get going. And hopefully, you guys will enjoy the content. I just got done doing some very tedious parameter mapping. So you guys will understand what's going on with that here in a minute. Um, but just to kind of give you a brief introduction to what I'm actually doing, here is my topic proposal. So this is going to be my senior research project. I have to do this in order to graduate with my undergraduate degree in physics. And so what I'll be doing, as you can see in the title, is generating a beam tune for the Triangle University's nuclear laboratory and a software called Cozy Infinity. So, in honor of us doing some particle physics, I've got my standard model t-shirt on here. Super stoked about that, and the NASA hat. We always got to have the nerd gear on. And so, what are we going to be doing? So, if you look at this motivation here, you'll see that I talk about how Tunnel is going to be getting some upgrades to the high energy end of their beam line in the next few years. So Tunnel is a particle accelerator laboratory that conducts particle and nuclear physics experiments. It's on the campus of Duke University, where I am hopefully going to be attending for my PhD in a few years. We'll see. And so they're going to be getting some upgrades. And my professor, Dr. Daniels, when we were fishing around ideas for my senior research project, was like, hey, I have this colleague at Tunnel, Dr. Longland, who is at NC State, and he was thinking, since they're getting ready to get all these upgrades, it might be a good idea to make sure that the beam is still tuned and calibrated optimally. And so the idea was that when Dr. Daniels did his graduate research there and Dr. Longland did his graduate research there, the beamline that they worked on was tuned by the older gentleman that already had been working at the lab since the 60s. And they never really questioned it. They just took it as it was and ran their experiments. And so his idea is, well, now that we've got this updated computer software called Cozy, which allows you to model uh, particle accelerator beamlines, why don't we, you know, code up the beamline and simulate it and tune it and compare that to what the previous tunes were. So the goal effectively is to compare and contrast our optimization of the beam tune to the old optimization and see if it needs to be changed. So how are we going to be doing that? Well, what we will be doing is using this software called Cozy. So if I go into my Linux terminal here and pull up Cozy, this is Cozy. So it's a software that runs in the terminal, and you write the code for Cozy in just a standard old text file, which I'll be doing in VS Code. And then you, as it says, give it the source file name, and that will generate the PDF picture that it draws, and then you can extract things from there. So just to show you one of the files, we'll run my professor's file, and it tells you that it reads it and it executes it. That's how you know it was done with no errors. And then I can just say, for example, xdg openpick1. This is not the 52deg file. This is one of my other files, but it just opens this PDF. And as you can see here, we've got just pictures of what the elements are. So this is a quadrupole, this is an aperture, this is an aperture, this is a dipole magnet, and then you can see the green lines are our beam. So that's what we'll be doing. And so, like I said, I'll be doing my text file in VS Code. So I'll go ahead and pull that up. So this is one I was working on last night. So I'll keep that open for just a second. Oh, cat's trying to give me technical difficulties. So I will keep this open and to the side, just so I have something to refer to. Drop it, yeah, cool. And so then now I will go ahead and do a new text file. And we can just close out the terminal for the time being because we don't really need it until a little later. And so what I need to do now, right, is I have finally, so we went to Tunnel over Christmas, and we went on a beamline safari, as my professor likes to call it, where we basically went through and we mapped the entirety of the beamline from end of the high energy accelerator all the way to where the beam stop is. And what we did was we wrote down every element on the beam line and their distances so I can put it into Cozy. And so the way that this works, as you can see here, is first line we need to write is include Cozy. And so I'll go ahead and do that. With a colon. So all the colons are because this is a Fortran compiled program. So it writes like a Fortran script. And so now I need to give it a procedure. Okay. And so the way that this works is I say I have a quadrupole, a drift length, a quadrupole, a drift length, a quadrupole, a drift length, a quadrupole. And so I tell it the length of my quad, field strength of my quad, which I'm leaving as a free parameter so I can write it in and change it down here, and then the aperture of my quad. And then I tell you the drift length between each quads, and then another drift length, and so on and so forth. And so that's the procedure. And so it's going to be interesting here. Now I'm going to go and I'm going to look also at my professor's original text file here. Because again, I've never coded in this thing before. Well, I have now, but prior to this. And it's not exactly like Python or Fortran where you can go on YouTube and find tutorials. It's a very niche software. It's not open source. You have to get permission to use it from Michigan State, what have you, etc. So let's see. So this one here. So you don't have to code in aperture, so that's good. So I think what I need to do is I need to tell it that there's a quadrupole, a drift length, a quadrupole. So I basically just need to code in the procedure into the quadrupoles. And so that might be a little bit irritating based on how I did my sheet here. But that's the point of this YouTube series. You guys can kind of see what this research is looking like and how it's going. And so I'm going to call this procedure. We'll call it 6 quads. Since I have 6 quads, I need to code in. And they're going to be A, B, C, D, E, and F. 6 quads. And so now the command for a magnetic quadrupole is MQ. Pretty straightforward. Now the length of my first quad, 0.287, has a field strength of A and an aperture of 0.025, colon. Then, Cleo, honey, sorry if she's meowing a lot, guys. She's very uppity today. Now I need a drift length. So my drift length between the first quad and the second quad is 0.5 meters. So I'll do drift length 0.5. Or no, sorry, that's 0.05. I wrote that wrong in my sheet. But fixed it where it mattered. So, all right. And then next up, we will have another quad. This one's length is 0.298. Field strength B, aperture 0.025. Colon. And now another drift length. So now the drift length between quad 2 and quad 3. Well, we're going from third quad is positioned at 9.22 meters, and the end of quad 2 is positioned at 1.568. So we'll have a drift length of 7.652 meters. And I'll have a field strength C and an aperture of 0.025, colon. Oh, oops, there's no, that's not a magnet, that's just a drift. So just drift length, colon. Okay, next up we have the third quad, so MQ, and it has a length of 0.381. Field strength C, aperture 0.025, colon, and give me one sec, guys. I'm gonna go feed my cat. She's yelling at me. Come on, darling. You guys are coming with me because I have the mic on my shirt, so won't take long. Feel free to skip this part of the video. It'll probably take about 20 seconds. There you go, darling. Now, hopefully she won't be incessantly meowing in the back of the video, because I'm sure that would be annoying to you guys. All right, back to it. Now, we just coded in quad 3, and we put in its length, so that's good. And now there's a drift between quad 3 and quad 4 of 0.051 meters. So drift length 0.051, colon. Now we've got quad 4, which has a length of 0.356, field strength of D, and an aperture of 0.025, colon. And then next up, we're going to have to put the drift length between the end of quad 4 and the beginning of quad 5. So that's going to be, oh, well, I have it here. Great. So it's 3.289 meters. So drift length, 3.289, colon. And now we have quad 5, so MQ. This one has a length of 0.203 meters, field strength E, aperture 0.025. Sorry if this is a bit redundant. Then I have a drift length quad 6 of 0.280, colon, and quad 6, which is going to be same length, 0.203, colon, and field strength F, aperture 0.025, colon. Now we can end the procedure. And so what I did in my other one was I indented these a little bit so I could see what's going on. So I'll go ahead and do that and make it pretty. Now the next line will be end procedure. Oops, thought you were going to finish it for me. Yes, code. So there's end procedure. Okay, and now the next thing we need to do, oh, it's highlighting my text now. That's interesting. Does it think I'm in Python or something? Because I'm definitely in a text file, but all right, I'm not going to complain about highlighted text. All right, now we're going to do procedure run. So now is where I go ahead and put in some dummy. So first of all, I got to tell it what my variables are. So I have variable q1 1 colon variable q2 1 colon variable q3 1 colon variable q4 1 colon and then q5. And so now I'm just giving all of my, so these are all open parameters, and now I'm just telling it that these 6 parameters, these 6 variables are going to be called q1, q2, and so on. And then I'll give them actual field strings in a line like this. And then so this would be variable q6. And now that that's done, I will actually copy and paste this over. Copy and paste. And then I'll just add in q5 and define it as the same strength, and q6 and give it the same strength. Okay, so now that's done. So now I have this order thing, right? So this basically is the order of the phase space. It's the order of the approximation COSY uses. So it's the 5th order. 2-dimensional phase space, 0 external parameters. That's what my professor wants it to be. Now, RP is our reference particle. So the 20 is the energy. So it's going to be a 20 MeV proton because it has an atomic mass of 1, and it's going to be charge plus 1. So that's what the input is for this argument: energy, mass, and atomic mass units, and charge. Colon. SB. So SB is basically, well, let me just pull it up and tell you because I'm kind of forgetting myself. I have this reference manual. So if we go here, oh, it's pulled up right here. So it's the half widths of the beam in all these different directions of phase space. And then it also takes care of the off diagonal terms in the matrix, in the transport matrix. And so what we have is we have something in X and A and Y and B, and then zeros across the board. So I will be able to tell you more about what that means as I get more into the research, because it's the beginning of the semester. So part of the project is I have to dig into the theory as well and understand what's going on. And so if I can give you a brief rundown, effectively the idea of what COSY is doing is you give it a beamline with initial parameters, and you treat it like a geometric optics problem, right? So you have a matrix, right, that takes in all your beam parameters for the initial conditions, and you have a starting matrix. And then each element can be treated in COSY as another matrix, or a transfer map, as it's referred to. And what it does is when you multiply the beam initially by the matrix of a quadrupole magnet, it maps into a new matrix which has the beam after it's been through the quadrupole element. And so that's how COSY stacks these things and sends it through elements. So it's just some optics. The only thing that's different is we're not sending light through a lens. We're sending, a charged particle beam through a lens. So it's a little bit different, obviously, but the physics can be thought of as the same. So this next line, CR, gives us a unitary map at the start, and it clears all the rays that may have been in there from the last run. ER is giving us our ray ensemble. So again, I will have more to say about that as the semester goes on. And then this BP is going to begin our picture. So this is the part that's going to be different. So the way that I had it before is I had an initial drift length, and then I had my 4 quads in a row, and then I had a drift length, and then that was the end of the picture. And so now I've got to draw a picture with lots of stuff in it. So come here, darling. You're being so noisy today. Hopefully she's not generating a bunch of noise in the video and irritating you guys. Usually she's quiet, but she is getting ready to get fixed, so she's in heat right now, so she is a little bit noisy. But anywho, back to the physics. So we've got to draw this picture. Okay, so it's going to start with a drift length. First thing we'll have is a drift length of 0.933 meters. And then we have our first quad. So now we'll say Q1 colon. And then we have a drift length of 0.05. Let me just refer to this real quick to make sure. So the quads in his original were back to back, so that's why they have no drift length between them, it seems. Well, I guess I already coded in the drift length up here, so I can just put them back to back. So that should be, I'm thinking that should be fine. However, I'm just going to put a drift length in the picture to just see if it changes things. It's kind of a trial and error. So now we have Q2. And now, wait a minute here. Is there anything? No, there's no parameters with it. Okay, that's what I thought. Okay, so now we're going to, we've put in Q2, and now we have a drift length of 1.632. 1.632 colon. And then we have a horizontal aperture. So now I have to call that app. Now I have to refer to this other one because I didn't have any in my last night version. So now the aperture, you give it the, it's a rectangular aperture is what the 1 represents. And then the openings on the aperture are given here, X and Y openings. And so what I'm going to do is I'm just going to take this 0.013 and put that for all the apertures I have in here. That's obviously not how they're set, but those are one of the things we're going to tune. So, I'm just going to leave it as what it is for a trial run. So we will say aperture. I want to make it easier. I will just call it 0.01, 0.01. And 1 because it's rectangular, and then I will just copy and paste that as we go through, because now we have, let me get my pen so I can make sure I don't lose myself here. So we did quad 2, and then we did drift length, horizontal aperture. So that's where we're at here. We need this drift length here. So it's going to be 0.737 drift length. And then another horizontal aperture. So hopefully 0.01, 0.01, 1 colon. I'm just going to go ahead and copy and paste that line, so I'm going to have to be doing it a bunch. There's more apertures than anything in this document. So there's that. After the aperture, we have another drift length of 0.152. 0.152 colon, and then we have after that another horizontal aperture. So I'll just go ahead and paste that in. We have another drift length of 1.067 and colon, and then after that we have yet another aperture. So glad I did that copy paste. Then another drift length, and that's going to be 1.245. And then yet another aperture. And another drift length. This drift length is going to be 0.152. Oops. And then we have yet another aperture, and that's going to be followed by a drift length of 2.667. And then we have another quad. So we'll have quad 3. And that's going to have a length that's already set. And then we have a drift length of 0.051. And then quad 4. And that length is already set. And then we're going to have a drift length of 3.289. And then we're going to have quad 5, Q5 with a length that's already set. Missed a colon. And then after quad 5, before we get to quad 6, we have 0.280 as our drift length. Quad 6. And then drift length, we're almost there, guys. 3.251. And then an aperture. Put in the aperture. So that's where I'm at now. Drift length 0.025. Aperture. Drift length, aperture. Drift length of 1.321. And then another, you never guess what's going to come next. An aperture. Then that's followed by a drift length of 0.045. And then, of course, another aperture. And a drift length of 1.117. And then an aperture, followed by a drift length of 0.007, LOL. After that, there's going to be another aperture, followed by a drift length of 0.704. And the last thing we'll have in here is the end of the beam, which will just be an aperture with dimensions of 0, so it'll kill the beam. And that is it. So that's a lot. I think my timer's just about to go off, but I'm going to see. Yeah, it is. I'm just going to see if this will run. And if it doesn't, hopefully we get it running in the next video. And so then I will just say end picture. So the next command will be EP colon. And then PG minus 12 minus 12 gives me my PDF. And then I hit it with an end procedure, colon, and then run, colon, and colon. That should, hopefully, work. And so now I will save this as full beam trial run, and then I have to save this as a text file, or not a text, a Fox file. And it's going to save into Cozy. Save. Now I'll just go to my files, make sure it looks how I want it to. what did I call it? Full beam trial run.fox. Okay, so there it is. Well, moment of truth here, guys. We'll throw it into the terminal here and see if it works. So full beam trial run. So here we go. Cozy full beam trial run. Well, didn't seem to like that. Maybe it's case sensitive. Maybe I need to name it something that's not all caps. Yeah, it's because I did dot capital Fox. That's why. I can name it full beam trial run. But it has to be dot lowercase fox. That's why it didn't run it. So full, oops, still in the full beam trial run. Fingers crossed, no errors. Ooh, boy. Lots of errors. All right, guys. I will figure this out and get back to you. But now you know what the research is really like. It's just a bunch of trial and error. So you guys take care. Have a good night. See you later.